Now let's start with the electric field intensity at any point due to short electric dipole. Now, I am talking about the electric field intensity at any point. Till now, we have discussed the electric field intensity on axial line, on equatorial line and so on. But now we are going to discuss that when any charged body is placed at any point around the electric dipole, then in that condition, what is the electric field intensity? Now, let's start with the derivation. For that, we have to consider the dipole. Okay, this is point A and this is point B. At point A, there is a charge that is minus Q, and at point B, there is a charge plus Q, and it is separated by a small distance. So, this is called electric dipole. Now, there is one point, let's say this as capital K. Okay, this capital K is placed anywhere. Okay, it is kept anywhere around this short electric dipole, and you have to find the electric field intensity around point K. Now, in this condition, first let us take the distance of K with that of the center of the electric dipole. The center of the electric dipole is, let's say, represented as capital O, and the distance of K with that of O is given as small r. So, this is the distance, that is KO is given to you small r. Now, this line, that is KO, is making an angle theta with that of the AB. That is, this point K, which is placed anywhere around this electric dipole, is making an angle theta with that of the electric dipole, which is shown by the line that is AB. Now, in order to proceed further, you have to consider very important points. The first important point is that we have to go into the derivation that we have already done. That is the axial line and the equatorial line. In the axial line, we have seen that the electric field intensity, capital E, is given by 2kP upon RQ. This is the electric field intensity that we have already calculated when the electric dipole is of very small length. In this condition also, our consideration is that the dipole length should be very, very small. So now, this is the formula when we have considered the axial line. Second is the formula that we have already derived, that is Kp upon Rq. This is the formula when we considered the equatorial line. Now, these are the two formulas. Referring to these two formulas, we have to divide AB into the axial line and the equatorial line. You have to resolve AB into their respective components. Electric dipole is not a vector quantity, so how we can resolve it? We are not going to resolve the electric dipole. In fact, we are going to resolve the electric dipole moment. There is a word electric dipole moment, that is P with a vector sign on it. Now, you can see here that in this particular formula, there is a vector quantity P. This is your dipole moment. Again, in the equatorial formula, there is another P with a vector quantity. It is also a dipole moment. That means if you have to resolve or you have to indicate the electric dipole with some vector quantity, so you have to take the help of a dipole movement. I am asking you to resolve vector AB. So in that condition, you have to go into the dipole movement. Now, this dipole moment is resolved into y-axis and x-axis. How we are going to draw the y-axis? Now, see, this is a horizontal line. If in the condition I have to make a y-axis, so this is a y-axis for the vector P, which is the horizontal line. Similarly, I have to make the x-axis. So this is your x-axis. Now, you can see from the diagram that this y-axis and this x-axis is at 90 degree to each other. That means we can say so that this and this are the two vectors which are resolved by the dipole moment, which is represented by P. Now, you already know that how the vectors are resolved. In this condition, first we have to look that what angle this dipole moment is making with the x-axis. This is a dipole moment, this hole is a dipole moment, and this hole is a x-axis. So this angle that vector P is making with that of the x-axis is your theta. Now, if this angle is theta, so y-axis, this is the y-axis for the corresponding vector, it becomes vector P sine of theta, and this is the x-axis for the vector P, so it becomes vector P cos theta. This is the way where we have resolved the dipole moment into their y component and the x component. Look at the diagram very carefully. In this diagram, you can see that this K lie on the x-axis of the dipole movement. So now let us mark these two vectors as the different electric dipole. That is, if I am talking about the x-axis, so let me mark it as A1 and this particular point is B1. So again A1 and B1 becomes the dipole, electric dipole, which is resolved in the x direction. Similarly, we have to mark this particular vector, this particular line as, let's say, A2 and B2. Now you can see here that A2 and B2, this also becomes the electric dipole of the y-axis of the vector AB. Now you can see from the diagram that the vector AB, this is electric dipole, okay, and the dipole moment is P. So this AB is resolved into A2, B2 and A1, B1. Referring to this particular figure, can I ask you a very simple question that at point K, can we use axial line and equatorial line? Yes, we can use, but how we can use, you can see here at point K. Now look, A1 and B1, okay, just measure point K with that of A1 and B1. A1 and B1 now turns at the axial line for point K. That is, point K now lies on the axial line of A1, B1 electric dipole. In that condition, it produces the resultant electric field at point K, which is, let's say, represented by E1 vector. Similarly, A2, B2, you can see here, A2, B2 is a perpendicular line for point K, and this perpendicular line can be represented as the equatorial line for point K, and we already have worked upon the equatorial line. So A2 and B2 will provide the electric force at point K. Let us represent it by, let's say, E2. So E2 is the vector quantity which is provided by A2 and B2. Now, we got the two electric fields, that is E1. E1 is the electric field provided by A1 and B1. This is the axial line. Similarly, E2 is the electric field which is provided by A2, B2, which is the equatorial line. Now, using the same concept, you have to find E1 and E2. Now, let's work upon it. If I have to find E1, okay, E1 is the vector by A1 and B1. So, the formula in the case of axial line is given to you, that is 2kp upon r cube. This is along the axial line, so this is the formula. But along A1, B1, the quantity of the dipole moment is changed. This quantity is no longer P, it becomes now P cos theta. So instead of P, you have to put the value P cos theta. So it becomes E1. This is the electric field created by A1 and B1. Similarly, you have to find the value for E2. Now, this E2 is the electric field which is created by A2 and B2. So it is created by A2 and B2. And what is this A2 and B2? This becomes as the equatorial line for point K. So we already have worked upon the formula for equatorial line. Now using the same formula, we have to put Kp upon R cube. But in this condition, along A2 and B2, the dipole moment is changed. Now it becomes P of sine theta. So instead of P, we are going to write P of sine theta. So this is the first equation, this is the second equation. Still we haven't found the resultant at point K. In order to find the resultant at point K, you have to use the parallelogram law. Now this is the resultant at point A, which is given by vector E. Okay, if you complete this whole figure, so this becomes the diagonal of this parallelogram. So the resultant at point K is given by a vector E. And what is the formula for it? It becomes under root E1 square plus E2 square. Okay, the angle between E1 and E2 is 90 degrees, so cos 90 degrees is 0. So remaining term is 0. That's why I've written only E1 square plus E2 square. Now, putting the value from equation 1 and equation 2 into this equation, you will get your answer. Now, let me solve it under root E1 square. So it becomes 2kp cos theta upon r cube, and this whole value becomes whole square plus E2 square, that is kp sin theta upon r cube whole square. So I use the value 1 and 2 and put it in the equation, that is E is equals to under root E1 square plus E2 square. Now on solving further, we will get that E is equals to, okay, what we do that all the common terms from these two, we will take it out, okay. So it becomes kp upon r cube outside the under root. Inside now it becomes 2 cos theta. 2 cos theta is left, so now we can write it as 4 cos square theta plus. Here sin theta is left, so it is written as sin square theta. Now on solving it, that is kp upon r cube, it remains like this under root. If we expand these two equations, so we can get 3 cos square theta plus cos square theta plus sin square theta. Now you can see here cos square theta plus sin square theta is equals to 1. So this equation becomes kp upon r cube under root 3 cos square theta plus 1. So this is the electric field intensity at any point with respect to the electric dipole. Now this is the electric field intensity at any point. Now moving further, if the resultant of electric field intensity is making an angle, let's say beta, with that of the x-axis, so you have to find that what is this angle, that is you have to calculate beta. From the same principle, that is the parallelogram law, there is a formula for tan beta also. In this condition, the formula is E.Y upon E.X. So what is E.Y? The E.Y as compared to the resulting electric field intensity is E2. So it becomes E2 upon E1. We know the value of E2 upon E1 if we substitute the value. So we will get sin theta upon cos of theta, and it is 1 by 2. So now according to it, if we solve it, so we will get your answer tan beta is equal sin theta upon cos theta, that is tan of theta 1 by 2. So this is the formula, that is tan beta. Beta is the angle which the resultant is making with that of the x-axis. So now these are the two values that are to be considered. There are various cases in which we have to work further. So now let's start with all the cases one by one. So these are the two cases that we are talking about. In this condition, what happened? If the K lies along the axial line, that is along A1, B1, so the theta, that is the K and the axial line, is making an angle theta and it becomes 0. So theta in this condition becomes 0 degree. And similarly, if you have to work upon this formula, so cos square theta, in this condition cos square 0 degree becomes equals to 1. Now put this value into this equation, that is E is equals to kp upon r cube under root 3 cos square theta. Cos square theta is 1, so the value turns to 3. Now it will become 1. 3 plus 1, 4 under root, so it becomes 2. So the value turns into 2 kp upon r cube. This is the electric field intensity along the axial line. We already have worked upon it. So you can see here that if you are considering at any point and theta is 0, this is the general formula, okay. This is the general formula for axial line as well as equatorial line. But if you put a very small condition, that is the condition is this, you will again get your same familiar formula that you have already calculated along the axial line. Similarly, if you put this value, that is theta 0, in this particular equation, so tan of beta is equals to 1 by 2 tan of 0 degree. What is tan of 0 degree? Tan of 0 degree is 0. So tan of beta is equals to 0, and beta is equals to tan inverse 0, so it is also 0. So now these are the answer, that is E is equals to this and beta is equals to this. Let's move on to case 2. In this condition, when K lies along the equatorial line. Now, when K lies along A2 and B2, so the angle K makes with that of A2, B2 is 90 degree. So now in this condition, theta becomes 90 degree. So what is cos square 90 degree? Basically, cos 90 degree is 0. So cos square 90 degree is also 0. Now, this value you have to put again in the same general formula. This is what? This is your general formula. Now put the value here, you will get E, that is equals to Kp upon R cube under root 3 cos square theta plus 1. This is the formula, okay. Now this whole value turns to 0. If this value turns to 0, so electric field intensity now comes to Kp upon R cube. Again the similar formula that we have already worked upon, that is along the equatorial line. Similarly, you have to put this condition in tan of beta. Now let me put it as tan of beta is equals to 1 by 2 of tan theta, that is 1 by 2 tan, it becomes now 90 degree. What is tan 90 degree? Tan 90 degree is infinite. So tan beta is equals to infinite, and what you have to do, you have to find out beta, which becomes tan inverse of infinite. So what is the answer? Beta is now coming 90 degree. So in this condition beta is 0 degree, and in that condition beta is 90 degree. So these are the two conditions that we've already worked about, and this is the general formula of the electric field intensity at any point.